So hello everyone, my name is Avinash. I'm currently pursuing MTech in quantum technology from here. So next speaker is Mr. Rohit Ramakrishnan. He's currently researcher at Applied Photonics Lab in Department of Electrical Communication Engineering at ISC. And he did his PhD in the high dimensional quantum technology using photonics. And before that, he was a research assistant at Central Quantum Technology of National University of Singapore, and where he worked on quantum satellite project. And before that, he worked on quantum optics research group at Australian Defence Force Academy, and he also co-authored a book in the Quantum Internet, the Second Quantum Revolution, published by Cambridge University.
So good morning, everyone, and thank the organizers for inviting me to give this talk. So my talk is supposed to be a very basic introduction to quantum communication. So those who are already familiar with quantum communication to a certain technical detail might find a bit repetitive, so please bear with me. In particular, we will talk about quantum internet towards the end. So the title is a Quantum Internet, a New Frontier. So before beginning the talk, I would like to ask you a question. What happened on 29th October 1969? That's a date very important in the history of mankind, maybe. So what happened on that date? Yes? Louder. Not World Wide Web, but you are close to the answer. Yes? Yes. The first message was sent over the internet. So this happened in 1969 in USA. The researchers assembled in Los Angeles and Stanford. So a group of researchers, those days, computers were not like what we see today. Or the researchers at that day had a very sophisticated set of equipments according to the standards of the day. So they were stationed in Los Angeles and Stanford, and they were trying to send one word from one computer to the other. And this word was login. That is L-O-G-I-N. That is login to another computer. So this was a very challenging experiment at that time. So they had telephone connections between them. So they can check whether the other party has received the message properly. So they first set up the equipment, typed the letter L, and over the phone they asked, "Hey, can you see the L?" And from the other side came a very excited voice. "Yes, yes, we can see the L." They typed O, again over the phone. "Can you see the O?" The reply came, excitement was doubled. "Yes, yes, we can see the O." They typed G, and system crashed. But nevertheless, that was the first message sent over internet. Or in a word, internet was born that day. Now, 50 years later, we are talking about quantum internet. In an era where internet has changed our lives more than anything. There's a saying like people used to predict in the past, when asked about the future of technology, people used to predict about International Space Station, moon travel, or travel to other planets, and even artificial intelligence. But nobody has predicted the internet and how it is going to change our lives. So today we are in an era where even the speed which we have right now is not enough. We are looking for more and more speed, better security, better facility, and this push is going on. And we started talking about the quantum internet. So what is it all about? So a quantum internet, similar to the classical internet, will be an interconnected network of quantum computers. They will be sending quantum data from one point to another. Just like instead of classical data. So instead of classical bits, we will be sending qubits from one point to another. So what is so special about it? In fact, we still don't know the potential of a quantum internet. Just like the guys in 1969 couldn't envision what internet will take them 50 years later, we can't actually right now predict what is the impact of quantum internet in another 50 years. But still, it promises a very high amount of security. In other words, unbreakable security. Suppose if I want to transmit some information to you, like say I'm trying to purchase something, and I'm passing my credit card information. I don't want anybody to eavesdrop into it. So quantum internet or the quantum communication provides me security so that even if an eavesdropper with another powerful quantum computer cannot break into it. That is one application. Again, this is just a starting. So we can do quantum key distribution to make communication secure, which is already being deployed. In other words, we can also harness the power of quantum computers over the internet. Suppose your university has a highly powerful quantum computer or your research center, and you are sitting at home. Using a quantum terminal, you can log into the university or the research center quantum computer and do the quantum operations. And even this data is going to be completely secure. So somebody who is doing research in, let's say, medical field, trying to simulate a new medicine, they can run the simulations over a quantum internet, over the quantum computer, without even physically having a quantum computer at their disposal. So these are the promises. So let's see how this things comes into picture. So just a quick review of qubit. I think all of you are familiar with this qubit, but still for the kind of review. So it's a classical quantum version of classical bit, where 0 becomes Dirac 0 and 1 becomes Dirac 1. And unlike classical bit, it can exist in a quantum superposition. The state of a qubit is given by phi is equal to alpha 0 plus beta 1. I'm not going into details because it was explained in the previous talk. So the property of qubit is that if you measure the qubit, it is not going to give you the value phi. It will give you the value either 0 or 1. In fact, it will collapse. All you can get is the probability by which it goes into 0 and probability by which it goes into 1. So this is a method of visualizing a qubit. We call it block sphere, and this is just a tool to visualize. The real physical qubit doesn't look anything like this. Okay. Okay, now, once you have the quantum bits, now we need something to manipulate the quantum bits, something to play around. So just like classical circuits, when we start with bits, then we go to gates. So here now we need quantum gates for something to manipulate the qubits. So there are two types of quantum gates in our discussion. That is single qubit gates and multi-qubit gates. Single qubit gates, as you can see, they just work on a single qubit. For example, this particular qubit. If a quantum gate, what a quantum gate does, it takes this value of a qubit and changes it to some other point in the sphere. Based on what operation we want to, what kind of rotation we want to have, we define the quantum gate. For example, it's a NOT gate. Let's say X gate. And to the X gate, you are inputting a qubit where psi is pointed in this direction, where the value is 0. So after the passing the NOT gate, the vector is going to point in the downward direction. It just inverts the quantum gate. Similarly, you can do all kind of rotation. And another important type of quantum gate is Hadamard gate, which actually takes a deterministic output and spits out a random output. What it means that, suppose this is the qubit which we are having, we pass it through Hadamard gate, it will place the vector exactly halfway between 0 and 1, which means when you measure it, it's going to collapse into either 0 or 1 with equal possibility. And this we will use in a lot of cases. Let us come to multiple qubit gates. So we have one gate or C0 gate, that's the basic gate. And C0 gate is almost similar to what we have learned as a NOT gate. We have a target qubit which will be inverted here, this is an OR operation. Addition to that, we have a control line for a control qubit. So this inversion will happen only if the control bit is 1. So whatever value is here will be reflected here, but only if it is 1, this will be inverted. Otherwise, this value will be reflected over here. And another extension of it is, controlled control notch or Toffoli gauge. Here we have two control lines and one target line. Sorry, I forgot, there's some typo, forgot this even here. Sorry about that. So here we have two control lines, and the inversion happens only if both control lines are 1. So the truth table is given here. So what is the purpose of Toffoli gauge? Why is it important? The answer is, Toffoli gauge gives us the quantum analog of classical gauge. In classical computation, we know that we call the NAND gate as a universal gauge. Why? Because we can realize all kinds of gates using NAND gates. And using a Toffoli gauge, we can build a quantum NAND gauge. Which means that Toffoli gauge is enough to perform any kind of classical operations. Similarly, we can do the quantum fan-out as well. Now, when we are talking about qubits, we are talking about the quantum bits which are also following the binary system. That is 0 and 1, we take it to Dirac 0 and Dirac 1. But in the Hilbert space, there is no restriction or there is no limitation that we have to stick to the binary logic. We can substitute 10 or even 100 or even 1000. You can go to any number. So when we change the base from 2 to some higher number, we call it high dimensional quantum information. Now we cannot call it qubits, but we call it Q-dit, where D is the level of systems. So instead of 2, you replace it with D. The value of D will be determined by the designer, like how much that's a question of your hardware. And you cannot visually represent a qubit. There is no tool like a block sphere to visualize it. Why qubit? The reason is that it's a very recent development and happened maybe less than 10 years. So the biggest challenge quantum communication faces right now is the data rate or the amount of information which can be transmitted. And it is nowhere comparable to what we have achieved in classical communication. So qubit is, some people, at least some teams believe that qubit might be a solution for that. Say for example, we have a qubit with a base 10. It can take 5 times the data of a qubit in one single quantum information. So by increasing the number of qubits, we can pack more quantum information into one single entity. But this is a very nascent field. Only researchers started, and the realization of qubits are a really challenging task. Now, what makes quantum information processing peculiar? There are some properties. I don't go into details of properties. I think it might have been discussed already in detail. But just a review. One thing you are sure about, quantum entanglement. I think you all know about what quantum entanglement is. Defined as non-local correlations exhibited by a set of qubits. Correlation means they are connected to each other, and non-local means the qubits need not be in the same location. So it's like tossing a coin in 2 different locations. If they are entangled, outcome of one coin will already determine the outcome of another. I think this is a familiar topic, so I'm not going to spend too much time. So now is coming to preparation of quantum states or entangled states. The Bell states are known as the maximally entangled states. And this is a circuit to realize a Bell state. We go with the Hadamard gate followed by a C0 gate. So we input 2 qubits and they get entangled at the output. So these are the 4 Bell states possible. And these are the maximally entangled states. And we use this as a resource in many of the quantum communication protocols. Again, another important theorem which we have to keep in mind is no cloning theorem. It is impossible to make a copy of an unknown quantum state. If you measure a quantum state, it is going to collapse. If you measure the qubit, get destroyed, and what you have right now with you will be a classical bit. But you cannot copy it without measuring. It's impossible. So, we have come across entanglement, no cloning theorem, quantum superposition. So now let us step into quantum key distribution. Quantum key distribution is of importance because this is the mature technology which has already hit the market, which has already been realized and being implemented everywhere. And this technology actually shows the power of quantum communication, how secure quantum communication can be. So there are different protocols to implement QKD, and what we will discuss is a very simple protocol, or the very beginning, the first protocol. So we have two units, Alice and Bob. And Alice is a signal source and a random number generator. Again, same with Bob. But in between Alice and Bob, there is a quantum channel as well as a classical channel. And this quantum channel is used to transmit the qubits for key, and classical channel is used to transmit the data. So, let me try to explain QKD in a very layman's language, that is, taking a complete abstraction. I'm removing all the mathematical or the quantum mechanical concepts, just to explain it in a very layman term. So people who are already familiar with BB84 protocol might seem a bit elementary for that, so please bear with me. So this is the situation. We have two parties, Alice and Bob, who needs to communicate something very secretly. They don't want anybody to eavesdrop into their communication. And we have a villain here called Eve. And Eve actually taps into their communication, try to eavesdrop them. So Eve is a great hacker. What Eve can do is, Eve can hack into any channel, read the data, and then replace it, or then replicate the data. So even neither Alice nor Bob has any idea this eavesdropper has come in between. The question is, how do they prevent it? Well, the answer is quantum physics, or quantum key distribution. So here we need two channels, a classical channel and a quantum channel. The classical channel will transmit classical bits, while quantum channel will be transmitting qubits. Now, to do QKD, Alice has to have a source which can generate a quantum information. So this particular source, so now to do QKD, Alice should have two sources of qubits which are identical, and let's say source A or machine A, which can spit out the qubits 1 and 0, and also another machine or machine B, which can spit out two qubits similarly like 1 and 0. The peculiarity is that by looking at the qubits, you cannot say from which machine it came from. Only the person who generated knows that from which machine they have taken the qubits. You cannot look at the qubits and say, okay, this came from A or B. Is that clear? Now, coming to Bob's part, the receiver. Bob also needs to have two detectors, detector A and detector B. Now comes the tricky part. Suppose the qubit generated from Alice machine A goes into detector A of the Bob. It will detect it perfectly well. So if it is 1, it will spit out 1. If it is 0, it will spit out 0. Now, by chance, if it goes to detector B, that is, qubit from machine A goes to detector B, the output is going to be completely random. Which means if I give this qubit 1 into that, 50% of time the output is going to be 0, 50% of time it is going to be 1. Equal probability. Similarly, this can be applicable to machine B also. Source B to detector B always will give you exact output. Source B to detector A will give you a random output. Is that clear? Fine. Now let us start the quantum communication. Let us first imagine the ideal case. Okay, there is no eavesdropping. Let us imagine the ideal case. So, Alice needs to select between these two machines. So this is done by a random number generator. In this case, let us assume a coin, an ideal coin. So Alice will toss a coin, and if the head comes, if head comes, Alice uses machine A. If it is tail, Alice uses machine B. Same with Bob. And this has to be agreed before the communication. That is, if head, we will go for A. If it is tail, we go for B. This has to be agreed prior to that. So now, Alice tosses the coin. If it is getting head, she will choose machine A. She will take the qubit from machine A. If it is tail, Alice will take the qubit from machine B and will put in the quantum channel. One more thing Alice will do, she will record every coin toss. That is in first coin toss I got head. Second is head, third is tail, just like that. She will keep a register for that, to record the coin toss. And now comes Bob. So Bob is receiving qubits, and Bob has no idea from which machine they are coming. So again, Bob has to choose the detectors randomly. So what Bob has to do? Again, use a random number generator, or use a coin. In this case, ideal coin. So Bob tosses the coin. When it gets head, he put it to machine A, detector A. When it gets tail, he put it to detector B. And Bob also records his tosses, like keep a register to record the coin tosses. Now let us think about it. Sit back and think about it. What is the accuracy that Bob is receiving information? It's a coin tossing, ideal coin. So 50% of time it will go to the correct machine, right? 50% of time it will go to a wrong machine. Now even if it go to a wrong machine, 50% of time it's going to be correct. So total we get 75% accuracy, right? So this is how the communication happens. They transmit all the qubits they want to transmit, let's say 1 million qubits or something like that. And now Alice and Bob has a register of 1 million coin tosses. So once the communication is over, Alice publishes this register or transmits this register to Bob. This can be done using a classical channel. There is no need of security. So Bob will compare his register with Alice's register, and whenever the coin is mismatching, the toss is mismatching, Bob will remove them. So after the removal process, only the coin tosses, which is exactly same, remains. Are you getting it? Yes or no? Okay. So now, once this registers has been synchronized, next is to check for security. So since we have already transmitted 1 million data qubits, we can compromise some 100 or 1000 qubits for that. So Alice will take her first 100 or maybe 500 qubits and put it in public or give it to Bob. Say that these are the values which I transmitted. And Bob has to compare it against his coin tosses. Now the coin tosser coincides. So therefore, Alice's first 100 qubits should be exactly equal to Bob's qubits, right? So this is how quantum key distribution happens without eavesdropping. There is no eavesdropping in between. Is that clear? Yes or no? Okay, now things getting complicated. We are adding the eavesdropper. Now things start to get a bit complicated. So as I told earlier, Eve is an efficient hacker. And let us assume that Eve has all the computing resources at her disposal. Eve has the most powerful quantum computer with her. So she can hack into any quantum channel. Now what will Eve do? He will take the data which is sent by Alice, and then how to read the data. Eve will also require two detectors, A and B. And how will Eve select between the detectors? Eve has to use a coin. Yes? So he will use a coin, use the detectors, and then get the classical value. This process actually destroys the qubit. So when Eve does the measurement, what remains with Eve is the classical value. Now, Bob knows that if a qubit is destroyed, Bob will know. So that means somebody has hacked into the communication channel. So to prevent that, Eve has to put the qubit back, right? So now Eve has to generate another qubit, similar to one which Alice has generated. So Eve already knows the value of the qubit, because she has read it. So she can generate the qubit, but the question comes from which machine? Eve will also require two machines, just like Alice. So here also he has no other choice but to toss the coin. So now Eve's coin, according to the coin of Eve, the qubits are selected and sent to Bob. So that's how the communication happens in terms of eavesdropping. Now think what is going to happen. There is no correlation between Alice and Bob's registers. Correlation between Alice and Eve's register and Eve and Bob's register. So when Alice and Bob compare the registers, remove the coin tosses where it doesn't coincide, or synchronize the registers, and then they compare the values. Are they going to be the same? Definitely not, because Bob's register is going to show the values generated by Eve's machines. And Eve's coin tossing cannot coincide with Alice's coin tossing. So that's how we detect these problems. So that's how quantum key distribution in a nutshell. It's a very simple problem. I mean, this is a very rudimentary form of quantum key distribution proposed by Bennett and Bessard in 1984 on this BB84 protocol. Now we have very sophisticated versions of QKD with higher data rates and higher complications. We can use entangled qubits for data transmission. Here we haven't used entangled qubits. The only property we have used is quantum superposition and no cloning theorem. Because you measures it, get destroyed. You cannot clone it before measuring. Because no cloning theorem prevents that. So that's how the QKD is working. Now let us look into the another form of quantum communication, the quantum teleportation. I think it was already discussed here, but those who are new to the topic, for the sake of it. So again, let us try to remove all the math and remove all the physics from that and try to present from a user's point of view. Let's say we are watching a movie, something like this. Say Mission Impossible 10. So when the movie starts, you see Alice and Bob working in some very secret facility. And they are preparing entangled qubits. They prepare one entangled pair, and they agree to take one qubit with each. So after generating entangled pair, Alice takes one qubit, Bob takes another qubit, and they leave the facility. And then the title starts to appear on the screen. And after the titles, the movie is cut to present tense. And in the present, you don't see Bob. Bob is a fugitive. Bob is hiding somewhere. Maybe the government disavowed his organization or something like that. Maybe like an Ethan Hunt, Bob is hiding somewhere. Now, obviously there will be somebody in Bob's previous organization who want to help Bob. So they want to send some information to Bob in the form of a qubit. So they approach Alice and give to Alice one qubit so that this qubit has to be transferred to Bob. Now, Alice has no idea where Bob is, but there is a communication channel between Alice and Bob, and that's a classical channel. And to Alice, the boss who is supporting Bob is handing over the qubit. Now Alice has two difficulties. What are they? First of all, through a classical channel, Alice cannot transmit quantum information. And Alice cannot measure this qubit also. Because if she measures the qubit, it will collapse. So then she cannot transmit the qubit. Again, even if she was able to somehow figure out what's the quantum information, still what exists is a classical channel. So the question is, should Alice choose to accept the mission or not? Well, quantum mechanics to the rescue. Anyway, the movie has to be a happy ending. So Alice definitely accepts. So what does she do? She takes that qubit, take it to her secret facility, and from her locker she retrieves the old entangled qubit which she has prepared with Bob. Now she has two qubits. She makes some quantum circuit to make them to interact them, and then pass these two qubits into the quantum circuit without measuring them. And at the output of the quantum circuit, she measures the qubit and gets two classical bits. It can be either 00, 01, 11 or 10. So these two classical bits she is sending to Bob. And upon receiving the classical bits, Bob takes his qubit, just made earlier, and performs another corresponding operation on that qubit. And which operation Bob is performing, that depends upon the data which Alice is sending. And what happens? The Bob's qubit becomes the unknown qubit which was given to Alice in the beginning. So that's quantum teleportation. With the help of a classical channel, you are transmitting quantum information, even though you are not physically taking one qubit to another location. Just transmit the quantum information. So, how does it look like in the circuit? This is how you do it. So this is a quantum entangled pair which Alice and Bob has generated. Passing it through a Hadamard gate and a CNOT gate, they're an entangled pair. And then here comes the unknown qubit. Alice takes her part and again pass it through this quantum circuit and do the measurement. And this value is sent to Bob, where Bob does the measurement and receives the unknown qubit. So that is how it looks in circuit. And how will it look in a lab? A quantum teleportation circuit looks like this. It's pretty messy. And this circuit can only transmit quantum information to a few meters. But don't worry, quantum teleportation, this protocol has been demonstrated to larger distances, including from Earth to space. So, we have seen, now we know what is quantum teleportation, quantum key distribution, entanglement, superposition, and, and of course, the working of qubits. Now let us step into the quantum internet. So just like 1969, some people were able to transmit a few words, a few letters, actually 2 letters, from Los Angeles to Stanford. Researchers in QTech Netherlands were able to transfer quantum information between three parties, Alice, Bob, and Charlie. Even though we are able to transfer qubit from one point to another, point to point we cannot consider as a network. To call it an internet, it has to be at least more than 2. So they made, it's a very humble beginning. So they have 3 parties, Alice, Bob, and Charlie. So what they first did was, Alice and Charlie has 1 qubit each, and Bob has 2 qubits. So step 1, Alice's qubit is entangled with Bob's qubit. So when a quantum entanglement happens between Alice and Bob. Okay. Then this actually acts like a memory qubit. Bob's second qubit is entangled with Charlie. Stage 2, Bob's qubit is entangled with Charlie. Stage 3, Bob locally entangles with both qubits. Now as a result, what we have a quantum entangle between Alice, Bob, and Charlie. So to realize a protocol, to demonstrate quantum communication, we require 2 things. One, a protocol to do how the communication happens. Second, a system to realize the protocol which we developed. So here, they first developed a system, and then they came up with some protocols. And they were able to demonstrate a couple of protocols using the 3 parties. And they were able to make a quantum entanglement between Alice and Charlie, even though Alice and Charlie are separated physically. These 3 are in 3 different locations in Amsterdam. So they were able to entangle between Alice and Charlie, even though Alice and Charlie, there is no connection between them, and they are separated. So we can consider this as the rudimentary beginning of a quantum internet. At least that is the claim. So, how do we take it from there? This is the state of the art in 2021, or 2022 maybe. So how do we take it from there? We have to build a global, how do we build a global quantum network or quantum internet? First thing we need is a quantum satellite, which has to make a global network. So this satellite is already there in the picture, even before quantum internet. 2016, China launched Mission 1 in 500 kilometer altitude, and they were able to show QKD, quantum teleportation, and also entanglement. So this happened in 2016. So this satellite could only transmit quantum information from Earth to a satellite and back. And now they are building the integrated space-to-ground quantum network, where there will be a quantum node in the space and corresponding in the ground network, they will having a space-to-ground network. So quantum internet is still in the very beginning stage, so we don't have a universally agreed format for protocols for quantum internet. It has to be formed in the next decade or so. And we know that our current internet, it works on TCP/IP, Transport Control Protocol and Internet Protocol. We don't have a quantum version of Internet Protocol now, because it is too far away. But there are proposals for a quantum transmission control protocol. Just like the OSI layer, which has 7 different layers, the first layer, from the bottom up, will be having the raw data. So that is what Alice wants to communicate to Bob, or any other parties. So this will have both quantum data as well as classical data. Upon that, you will have a packet which actually decomposes data into blocks, that is packet data, And associated classical packet headers will contain metadata. So this is the routing information. So here the data, the packet will have the routing information. Third comes the strategy. Strategy means how to route from one location to another by a cost optimization algorithm. Then comes the transport layer, where physical routing of packets arrive at the destination based upon the metadata in this packet. And transport layer has to ensure that they don't collide in the way and lose the data. Then comes the reconstruction. We reconstruct data from the received packets. Now, once the data is received, we had to make sure it is exactly the same what we wanted to receive. So we had to apply quality of service requirements. And here comes the quantum error correction codes, because quantum data can be corrupted. So if it is corrupted, we require error correction protocols to retrieve it. Then the final layer, service and application, is a high-level interface of data presented to Bob. And Bob doesn't have to worry about any of the quantum things happening in between. What he needs is just the information which he has. So that's the proposed QTCP stack. Just what we summarized what we said earlier. Physical layer with quantum data and classical data, packets, again headers, strategy is classical, transport layer is physical, and reconstruction, quality of service. This has to be completely quantum, because here comes the quantum error correction protocols. And finally, service and application. So that is the proposed version of quantum TCP, and we don't have a quantum IP till now. So from the hardware perspective, what all things require a quantum internet request? Sources, definitely to generate quantum data. Detectors, to detect the data. Memories, to store. Repeaters, and then some hardware platforms to realize. So right now, we can choose any physical system which satisfies certain conditions to carry quantum information. So right now, in terms of classical quantum communication, photons are the leading candidate. We were able to demonstrate a lot of protocols and a lot of achievements using photons. So photons are the leading candidate, and even the BB84 protocol, which I explained earlier, was demonstrated using photons. So if you are familiar with optics, when you think about machine A and machine B, think about photon sources which are emitting photons in horizontal and vertical polarization and diagonal polarization. Something is horizontal is 0, vertical is 1, and again diagonal polarization, similarly you can assign 0 and 1. So at the receiving end, you have again the same polarizer. If the horizontally and vertically polarized photon goes into the diagonally polarized wave bridge, 50% of time it will go into both sides. So that is only if you are familiar with optics. So here what we require is single photon sources. We have to prepare them on demand. And then entangled photon sources. We may not get the chance to, privilege to make entanglement at a later stage. So sometimes we will require entangled photon sources. And again, we have to build them in a semiconductor-based platform. Then again, satellites, they will also require sources on board the satellite. So we had to put the source on satellite, and they have to work in the outer space without supervision or without any intervention from us. Then comes the detectors. Again, for photons, you have multiplex photodetectors, homodynamic detectors, and practical photodetectors. Then comes the final building block, quantum memory. So quantum memory is nothing but just delays the quantum information for a fixed amount of time, a time which is user defined. So, for example, when quantum data packets reaches a bottleneck, the next part of the path is slower than wherever it came from. You have only two choices. Either they have to be stored and wait till the condition improves, or they have to be discarded. So if they have to be stored, they have to be stored in a quantum memory. And when they store in quantum memory, you have to make sure that they stay there for the required amount of time. And memories can be corrupted, because these are photons. External changes like temperature, pressure variations, everything can corrupt it. So the simple model of a quantum memory. We are transferring information from A to B and B to C, and we need the quantum information to stay at B for some time. So what we will do is, we will send it through a loop. and keep it in the loop as much as time we need it. Like in an optical fiber cable, imagine optical communication, we will have a fast switch where it puts into a delay loop. So it will rotate inside the delay till how much time we have to keep it there. Obviously, this switching time has to be much smaller than the delay time. And the time it can be retained in the loop should be an integer multiple of this term. So, as I said earlier, quantum memories are prone to errors. Just like any external change can cause errors. There are a lot of type of errors. So, according to the errors, we have to develop the quantum error correction protocols. So, one of the most common type of errors is the phase error. And phase errors are mostly caused by temperature and pressure variations and things like that. So we have defined, this is a work from our lab. We designed an error correction protocol to correct the phase errors. What we did was, we took the logical qubit and converted into a W state. W states are a non-classical states of light for photons. So we used a quantum Fourier transform to transform this qubit to W state. And then we introduced delays and random noises or randomly corrupted patch. At the receiving end, we pass through an inverse Fourier transform, and if the qubit appeared in the first two nodes, we call it success, and if the error corrupts them, it will be coming in the failure nodes. So it's a bit complicated in terms of mathematics, so I'm just abstracting whatever we have done. So from here, we detect only the failure nodes, because if we detect the success nodes, it will destroy the quantum information and it cannot be taken forward. So here we detect here. So if there is no detection, that means it is success. And if there is a detection, it means it's a failure. And we designed this protocol for both qubits and qubits. And then again, we try to experimentally validate them using experimental protocol, some experimental method. But unfortunately, we couldn't finish the experiment. And coming to experimental realization, we cannot use polarization for photons when it comes to qubits. Polarization is an ideal candidate when you are talking about qubits, but not for qubits. So this single protocol works for both qubits and qubits. So for qubits, we have to choose some other thing. So we choose orbital angular momentum of photons. And this is set up. We couldn't finish it, but the experimental scheme and the protocol, they are both published. So you can find it in the internet. And the last part is repeaters. That is, we need to repeat the quantum, repeaters are required to realize the internet. So they have primarily three functions. One is distributing entanglement. Just like we have seen earlier, we have to create entangled links between adjacent nodes. Then once entanglement is there, that improve the quality. We call it entanglement purification. Then entanglement swapping. That means already entangled links, we have to join together to form long distance links. These are done using quantum repeaters. And again, now the repeaters in the space, obviously satellites. They're an essential component when we talk about a global quantum network. So right now what we are having is a first generation satellite. China has already launched one, Singapore has already launched one. I had a chance to work on that. And India is building its own quantum satellite. So these are first generation satellites. What they do is entanglement distribution. You will have an entanglement source on board the satellite, and which will be coupled to two telescopes. So these telescopes will beam it to the ground, and then we can take the data. But to realize a quantum internet, this is not sufficient. We have to push it beyond. Right now, the focus on satellites is such that to make sure we can get sources working in the space. So once we establish that we can make sources and make them work in the space, we will require second generation satellites. Here we will have quantum entanglement generation, measurement, and also linked to other satellites. So here quantum data can be generated and also be measured. Also, we have to send the data to ground and also to the space, to other satellites. So to have a review of the paper, and we have published a review paper on quantum internet, a hardware review. It's a Springer publication, so you might need subscription to read it, but the free copy is available on arXiv and also ResearchGate. It's a quantum internet, a hardware review. Last part is, you need some integrated platforms to realize the whole thing. How do we materialize? Or which material do we use to do this? Frankly, we don't have a concrete answer. The research is progressing in all directions, and silicon is the leading candidate. The answer is the reason is obvious. We already have a well-established silicon facilities, fabrication facilities, so we can just piggyback on that. We don't need to establish extra facilities or to make quantum devices. But silicon has its own limitations when it comes to generating quantum, when it comes to qubits. So people are pushing a new platform based on lithium niobate. It has a built-in electro-optic effect. So lithium niobate is actually much more advanced, or we can do, gives us more functionality than silicon. But the fabrication technology is not as mature as silicon, so it is being pushed. There are other materials like diamonds, 3,5 group materials, and rare earth metals. These are all candidates of realizing quantum technology. Again, there is another review paper on the integrated photonic platforms. It's again a Springer publication. You can find the free copy in archive and also in the ResearchGate. And to have a detailed understanding of quantum internet, we have published a book, The Quantum Internet by Peter Rowley, and it's published by Cambridge University Press. So actually, Peter is a senior editor, and there are some 9 authors into it, and I'm one of them, contributed a couple of chapters. Right now, I think the book is out of print, out of stock, but soon the preprint will arrive. So I will summarize my talk. So we have started from basics of qubits, to basics of quantum communication to quantum internet. So, questions? Yes. Yeah. Okay. Just like in the internet, the classical internet, we require the repeaters, transfer data. So quantum internet basically works by transferring the entanglement. So memory just stores the quantum bit. It doesn't make the entanglement. So if you have to transfer entanglement to one point to another, you need repeaters. That's their function.
So how does the Blocksphere look for qubits?
There is no Blocksphere for qubits.
Okay, that's...
We cannot represent that.
Yeah, and then how do you measure what's the computational basis for the encryption, basically? When you have 2 different processes, process B, those are different bases, right? So how
for qubits, to perform cryptography using qubits, we will require new protocols.
Okay.
Not the BB84 protocols, they might not work.
So is there one or?
There are actually.
Okay.
We have proposed one. Again, it's still being tested.
So how do satellites work? Do they send a laser to come?
By laser tracking. They send over from the telescope to the Earth.
And they are precise enough to reach detectors, or are the detectors as like a satellite?
Exactly. They are precise. The challenge is in the last 1 kilometer. The distance is 500 kilometers.
Yeah.
Because I worked on the building of the first quantum satellite in Singapore. So when we try to model them, the challenge is the last 1 kilometer. Up to 499 kilometers, it will be perfect. There won't be anything. If data is lost, it's lost in the last 1 kilometer.
Last 1 kilometer.
And okay, we have developed methods to overcome that.
Okay. All right. Thank you.
Yes.
In almost every circuit, you use Hadamard gate, right? Like, why is that so?
No, the circuit which I explained was some basic things for BB84 and the other things. So it required Hadamard gate. Doesn't mean that Hadamard gate is necessary for all the quantum operations.
Okay.
It's a very important one. Most of the operators use them.
2 questions actually. How does it compare in terms of cost with the classical communication systems and
Well, right now the quantum communication is highly costly, and also it is nowhere in comparison with the classical ones. We still have to push it long.
And you mentioned about the data rate not being matched up to the classical systems. Is it more of a physics-based problem or a electronic
No, it's
technology?
a hardware problem.
It's a hardware.
It's an experimental limitation, basically.
Hello, excuse me, sir. Yeah. So, how different is the quantum channel compared to the classical channel? And is it possible for the quantum channel to destroy the state of the qubit?
Yes, of course. Noise in quantum channel can destroy the state of qubits.
Okay. And how different is it from the classical channel?
So let us imagine the classical channel. We are having optical fiber.
Yes.
We're transferring data using lasers, right?
Yeah.
These are photons that are carried. So your 1 bit of data is carried by a bunch of photons. It's a huge number of photons. When it comes to quantum communication, each photon will carry one quantum information.
Thank you.
I mean, it's a simple way.
Yeah. Sir, my question is, like if we proposed any protocol, for example, we have this baby84 protocol, and then we proposed another protocol that is PQC, based on PQC. So there is any software through which we can test this? Like for computer science student, we cannot move into physics lab and do all the simulations. So like what you suggest for us, like how can we test and detect like whatever we proposed that is working fine or not?
Okay. The way which we test is, we test it by mathematical way. So we just require pen and paper to calculate it. But I think IBM has put their quantum computer on the cloud, like you can access it by quiz.
But
I
sir,
have not tried it, but that might be a way, or once and it has to advance in much more way to test the quantum protocols.
For example, let us, I have to defend my PhD, for example. So I have to show all the simulations, like whatever I did. So we have we don't have that much access to the qubits and all. So all those are paid services.
Okay, as far as I know, there is no consensus in terms of software. And Python, I think people are using it mostly to simulate things, do things, but there are a lot of limitations. There is still no consensus, and different methods are being used. I had to check for which one works for your particular protocol.
Yes, sir, that's why I'm asking for specific, because there are so many.
That varies according to the protocol which we are developing.
Okay, so I'll discuss with you
For sure.
later. Thank you.
Like in the experiment which you conducted, I think for error correction, first you used the Fourier transform, quantum Fourier transform to convert into W states. So after that, what kind of phenomena or circuitry you used to separate the error ones and non-error ones into different qubits?
So it was realized using orbital angular momentum of photons. So we generate photons using spatial light modulators. And what we have to do is we have to program the spatial light modulators using LabVIEW. So we write the code and then transmit the photons. It is tested by the single photon detector unit, SPDC. And then again, we are testing only the failure nodes. Because if you test the success node, that means the quantum information is stopped there. So if you have to take it forward, we test the failure nodes. And if there is no detection, it means there is success. So it's a bit sophisticated, to explain it like that.
So if there are the bits incoming are completely correct, then the W state should be again converted into only the two two qubits. Which
So the experiment scheme is totally different like that. It's entirely different from what we have shown here. It implements the same thing, but the scheme is totally different. We can take the discussion offline if you are interested.
In that quantum internet you had shown, no, that three Alice, Bob and Charlie is showing. So here that Bob has two entangled qubits, one with Alice and one with Charlie.
Yes.
Suppose I want to go for four. Four people has to share something. So this is like something central, no controlling agencies there, like Bob and also something like if you extend to four people.
See, that's actually a question of hardware competency. So this is actually similar to the initial experiment which I described.
So this is not your protocol, or is it hardware?
It's a hardware. The protocol has been developed on this hardware. There are a couple of protocols which can be demonstrated using this particular hardware.
No, I am asking if the same concept has to extend to suppose 4, 5, like that number of people.
Yeah.
So then how it will go? So there should be a central somebody who will handle all these pairs, entangled pairs with other members.
Right now, as far as I know, there is no idea about that.
No
They're
idea.
still pushing it.
So it is still in that
It's
three
still
people
development.
stage.
It's a very beginning stage.
Okay. So with the one pair of entangled data, you can communicate how much ever data you want.
That is in the literature. I guess I don't remember the value, but I can get you the paper.
Okay. Thank you.
Sir, here. So with entanglement, right? I'd seen a video where you'd send a light to a pink diamond in vacuum. after about large number of photons are sent, some of them split and you get two entangled particles. In your experiment, when I'm doing communication of qubits, I don't have the liberty to send many bits for some of them to be entangled. So, I'm not a physicist, so I'm maybe wrong in this, how the entanglement is created. So, can you tell us how the entanglement is actually?
That's a bit sophisticated. Like we have to take the discussion.
Predictably, yeah, that's the. But is it correct that if that experiment is that if you send something through that pink diamond, one of those photons would split and you create an entanglement?
Not exactly.
Okay.
It's done using spatial light modulator.
Okay.
Which we can discuss later. I mean, that's
Okay,
a bit of a bigger discussion.
Okay, thank you.
Sir, one more question. You explained about that BB841 algorithm. First, Alice is generating the qubits. It's sending through the channel, any using photon or whatever you send. And consider you change that patterns of that qubits, and Bob receives some another patterns. Then again, as you said, they exchange Alice compares with what the Bob received, and Bob compares what Alice sent. Then how that is been exchanged first thing?
So that can be done in any way. We can do it using a classical channel.
Okay.
And we don't need any security there. There's only one party sending that.
Okay. Then there can be some same chances that you can manipulate when they are exchanging the key. You can manipulate every time and not let them establish communication only. Means connection.
See, Alice can make it public also. Instead of directly sending to Bob, Alice can make it public. Bob can read it from the public space and correct accordingly. Right. There are different ways to do that. Need not be one-to-one communication between Alice and Bob.
Thank you for wonderful talks.
Thank you.